Hello everyone, and welcome to a kind of a partial walkthrough through this free response. And so I've just redrawn the circuit for you here. And so we have a 30-volt battery. By the way, this is another symbol for battery. I'm not crazy about it because it's more lines that you have to draw. Less lines the better, but you get the idea. So we have a 30-volt battery, and it's connected in series to a resistor with 2 times 10 to the 6 ohms. Now, this resistor is connected in series with a capacitor that has a capacitance of 5 times 10 to the 8th farads. And there's a couple other things they tell us. They tell us it's separated by plastic, and this plastic is 1 millimeter thick, or just 1 times 10 to the 3rd meters. They tell us the capacitance. And they also tell us that each plate has an area equal to 1 square meter. Okay, and the first thing they ask us is, what is the dielectric constant of the plastic? Well, to get that, we know that capacitance is equal to epsilon naught times area divided by D. But that's when our parallel plates are separated by air or a vacuum. What's not written here is actually this dielectric constant K. For air or for a vacuum, K is 1, so our equation just simplifies down to epsilon naught times A over D. But when we have some other material in there, well, then we have this dielectric constant. But what's nice is they give us everything else in the equation. They tell us the capacitance, they tell us the area, and they tell us D, or the thickness between the two plates. And so doing that, I trust you'll be able to plug in and solve for it. You should get a K value of around 5.65. Okay. So it says it's connected in series, blah, 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 and switch S is open. And in the next part of the question, they ask us for the charging current, the initial charging current. Well, what that means is, right when I flip that switch, what's the current flowing into the capacitor? Well, the capacitor is connected in series with the battery, meaning that whatever current is flowing out of the battery is going to be the current that's flowing into the capacitor. Well, to get the current that's flowing out of the battery, we're just going to go V equals IR. I know the voltage is 30. I know the resistance is 2 times 10 to the 6. I can solve for the current. You should get a current of around 1.5 times 10 to the negative first, or excuse me, 1.5 times 10 to the negative 5th amps. That's our current. And again, to get that, we just did V equals IR. That's the initial current. Now, as that switch is closed, that current is going to get lower and lower and lower because the charge on our capacitor is going to get higher and higher and higher. The voltage difference across here is also going to get higher and higher and higher, because right when that switch is closed, the capacitor just acts as a wire. When the capacitor is fully charged, it acts itself like an open switch, killing the circuit. So, the next question says, what is the time constant? Time constant is just RC. So that's the resistance in the circuit times the capacitance in the circuit. So just take that resistance and multiply it by the capacitance. Pretty straightforward there. Next question. Determine the magnitude and sign of the charge on the bottom plate of the capacitor. Well, you know that plus, it's going to go plus, minus, plus, minus. So you know that our charge is going to be negative on this bottom plate. To get that charge, we're going to go C equals Q over V. We also know what the voltage is going to be across that capacitor. To get the voltage, we have to think about whenever it's fully charged, it basically takes all of the voltage of the battery and puts it onto the capacitor. So we know that our voltage across here is going to be 30 volts. So we know the capacitance, we know the voltage. All we have to do is solve for the charge. Okay, then the next question, how much potential energy is stored on the capacitor? Well, we know that potential energy is 1/2 QV or 1/2 CV squared. So you could use either of those equations to get the energy stored on the capacitor. But now the question changes itself up, and it says the capacitor is fully charged, but the sheet of plastic is removed, leaving us with just two metal plates separated by air. And there's a couple things that they want to know. Part C asks us, well, what's the new voltage across the plates? Part D is asking us, well, what's the new energy across the plates? Okay, well, to get the voltage across these two plates, here's what we have to think about. I started with an original capacitance, and I got that capacitance by K equals epsilon naught times area over D. Well, I have a new capacitance now, but that new capacitance, I'll call it C new, or Cn, is just going to be equal to the same thing, but now my K is equal to 1. And so I can call this Kn for the new dielectric constant, and I can think of it as a ratio. So Kn over K should equal Cn over C. My original capacitance, my original dielectric constant, my new capacitance, and my new dielectric constant. Well, Cn, if you look, Cn is just going to be C over K. My original capacitance divided by my dielectric constant. But how does getting capacitance help us solve for voltage? Well, I know that capacitance is Q over V. Charge doesn't change. No matter what type of dielectric constant I put in here, the charge remains the same. I don't lose any charge. What does change is the capacitance, and what has to change then is the voltage. So, to get the new voltage across my capacitor, I could think of it like this. You solve for the charge on your original capacitor, and you knew the voltage across your original capacitor. So, your new capacitance is going to also be equal to Q over the new voltage. So you could take this and plug it in to that equation. And you could take this, if you wanted to, and plug it into the old equation. But you know capacitance and you know the dielectric constant. So here we go. Q over my new voltage, which is what I'm trying to find, equals C, my original capacitance, divided by my original dielectric constant. Cross multiply and solve, and you can get a new voltage. Your new voltage that you should get is 170 volts. So I have a pretty dramatic increase in voltage. Now, what happens to my energy? Well, my original energy was 1/2 QV or 1/2 CV squared. Well, now I have the same amount of charge, but I have a much higher voltage. And to think about that, I have more potential energy now inside that capacitor. How? How did that happen? It took work to get that plastic sheet out. How much work did it take? However much more potential energy we have now. So yes, there is an increase in energy, but only because I had work put in by taking that plastic sheet out.